So now we're ready to look at logistic regression. So we're going to be looking at the logit, or log odds. It's an information theoretic way of defining what is gained when a decision is made. Let's review a little bit. So we have many observations, and each observation has features or factors. Then we base decisions on the features or the factors. And our strategy is to increase the odds of predicting the correct class of an unlabeled observation. We showed in the first video that if P is the probability of a positive, then this is the entropy for the resulting binary classifier. And the rate of change is the rate of change of entropy from before to after. And we're going to write this dHdt. We can write it in the form the natural log of P over 1 minus P equals beta of T. In other words, we can define beta of T to be dH dt over negative dP dt in this collection, this equation that we saw in the previous. And recall, we can only justify linear classifiers. So we're going to make a big assumption. Beta of t is a linear function of the features x1 to xn, or f1 to fn if capital X is in use. So our big assumption leads to the idea that better decisions will be of the form the natural log of P over 1 minus P is equal to this linear combination of the features. The coefficients are functions of time, but they tend to be on a slower time scale than the decision-making process. So for right now, we're just going to assume that they're constant. And so beta is this W0 plus W1 x1 up to Wn x sub n. We can solve for P, and we'll get P over 1 minus P is e to the beta, which means that the odds of y being equal to 1 is e to the beta. And then we solve further for P itself. We get 1 over 1 plus e to the negative beta, which means that the probability that y is 1 is 1 over 1 plus e to the negative beta. If beta is equal to a constant, so it's just the omega 0 term, then e to the beta is the odds of an observation being in class 1. Now let's suppose we look at the case of one feature. So beta here is W0 plus W1 x1, where x1 is a feature. And for now, we're only going to think about features whose possible outcomes are either 0 or 1. So for instance, x1 could be male, in which case true would be 1 and false would be 0. The data, therefore, is of this form. X1 has values A or B, which of course are either 1 or 0 right now, and then y is the class. Our model would then be of the form the odds of y given x1, P over 1 minus P, would be e to the W0 plus W1 times x1. And the probability P, you'll notice, is a function of x1. So if x1 is equal to 0, and the odds is e to the W0 plus W1 times x1, when x1 is equal to 0, we just get the odds of y given x1 is equal to 0 is e to the W0. But if x1 is 1, then the odds y given x1 is 1 is e to the W0 plus W1. The odds ratio of these two, the odds of y given x is 1 to odds y given x is 0, is e to the W0 plus W1 over e to the W0, and that's e to the W1. So therefore the log odds ratio is W1. It's the natural log of the odds ratio. Recall that the joint information difference is defined this way, and this W1, in this special case at least, is a measure of information. It's the joint information difference. What does that mean? Well, if y and x1 are independent, then the joint information difference is 0. And x1 is not going to be very useful in predicting what y is going to be. If y is totally dependent on x1, the joint information difference will be infinity, and this will be a fantastic way of predicting the class because of the total dependence. Now let's go back to our cross-tabulation or contingency table. We have y is 0 or y is 1 and x1 0, x1 1. We get the counts, and the odds ratio is P11, P00, P01, P10 in the denominator. We can think of that in terms of counts, and therefore W1 is the log of this ratio of products of counts. So let's look at an example. Y is in class dessert and X1 is gender. And remember, we had a female that did not get dessert, a male who did, a male who did not, and a female who did. Let's look at this in the IPython notebook itself. So we'll need the breast cancer and getting dessert files. I'm going to toggle the file browser now. And we'll need these, and later on you'll actually have an assignment where all these are included. Let's read into the dessert data. And now we're going to do a cross-tabulation, and here is dessert versus gender, and the cross-tab is just our two-way table. We're going to treat those counts as a matrix, and then our approximate odds ratio is given by this, and that's negative 0.066, and that's the log odds ratio. Now I'm going to do the exact same thing and use a classifier. In particular, I just applied the Logistic Regression classifier from sklearn, and notice that pretty much they're the same number. No surprise there. We have a log odds ratio of very close to 0. Now, just for the sake of looking at things, let's notice that the area under the curve here was 0.5. And so to put all this together, we saw that we could use the counts to predict the log odds ratio, the W1, and in the classifier coefficients we get the same thing. Let's look at another example. We have already looked at this Wisconsin breast cancer data. We see that there's 2 classes, malignant or benign, and 9 features. And we had 699 observations. And the size uniformity seemed to be very important. In particular, from the decision tree lecture, we got this decision tree, and the size uniformity, greater than or equal to 2.5, seemed to be an important issue in determining whether or not an unlabeled observation came from a malignant sample or a benign sample. So let's look at this size uniformity greater than or equal to 2.5. Once again, back in the IPython notebook. So I'm going to load in the data, and then I'm going to calculate the counts. And you can see that the size uniformity comes in 10 classes, so we're just going to look at the size uniformity in terms of greater than or equal to 2.5. And so notice this next one is only greater than or equal to 2.5, and there's our odds ratio approximation, our log odds ratio. I'm going to look at the classifier, and no surprise, it's going to give us the same log odds ratio. So we get W1 in both cases to be this 5.26832. So 5.267. So they're close. So they're not exact. They're not using exactly the same process. We'll look in the next video at this concept of maximum entropy. Let's see how good it is, however, as a predictor. So we look at our size uniformity, area under the curve, and there's our received operating characteristic, and we get 93%. Now in most applications, we'll have beta in terms of several features. And we'll interpret each W sub j as a log odds ratio. But what we really mean by that is if everything else is held the same except for the one W sub j, and the X sub j only changes from a 0 to a 1, then it's the log odds ratio or joint information difference with all the other features held constant. In most applications, logistic regression is used as a linear classifier. So this interpretation is helpful, but it's not the key concept. Let's go back to our iris data set. We saw this in the first lecture. So 50 samples, we have 4 features. And we first looked at this in terms of 2 classes, and we see very quickly that class 0, isotosa, and class 1, not isotosa, they're linearly separable. And now we have something that actually can do the linear separation. So what we're going to do is we're going to apply logistic regression to the iris data set using 2 features, sepal length and petal length. Class 0, isotosa, class 1 is not isotosa. Here are the actual Python commands. We would load the iris data. We get X is going to be an array, which is going to be the 0 sepal length and 2 petal length features for these irises. We're going to have the target. The classifier is going to be a logistic regression classifier. That's what this command does. We're going to do a fit, x comma y, and that means the classifier is going to learn or fit to this xy data training set that we give it. We're actually going to give it all the data for right now. And it will then estimate these coefficients in W0, W1, and W2 in this logistic regression. And then we're going to predict every point in the rectangle 4, 8, cross 0, 7. We'll color the point white if it's in class 0 and cyan if it's in class 1. Of course, we're doing this on a mesh, but it's a very fine mesh, so the result looks like we've done it at every point. And you'll notice that the logistic regression created a linear separation. Let's redo this using 3 classes. So once again, we're only doing 2 classes in the course itself, but 3 classes is not really a big deal. So here is our logistic regression applied to the 3 classes, and you can see once again we get the same linear classifier between the isotosa and not isotosa, and then logistic regression gives us another linear separation. This one is not perfect because the data is not linearly separable. It's just sort of the best we can do. So in summary, we could now build decision trees using logistic regression at each step. And that's because logistic regression is going to make linear decisions based on beta being a linear combination of the features. And it's based on all the features, not just one at a time. And we have an interpretation for each coefficient. It is a log odds ratio. And all of this will depend on the odds, p over 1 minus p.